Okay, similar to Gaussian mixture model, yeah, we will use multiple of these Gaussian components, but for each Gaussian component, we'll have the mean, which is the same as our data point value, and across all the Gaussian components, they share the same variance or standard deviation value. Okay, and then intuitively we can think of like having this envelope of each Gaussian component centered at each of our data items, right? And then altogether, if we just sum them up along the vertical lines, and then the total density plot will be drawn as this blue curve. Okay. So in this case, what is the number of parameters in this case? So which parameters should we determine based on our data item? 아, 네. 그럼 이거를 다시 저 밑으로 뽑아서 근데 이것도 되게 이거
이렇게 운전하시면 여기서 쓸 수 있으니까.
아, 네.
제가 아니면
네.
쉬는 시간 하시면.
네네. 제가 그럼 이따 하겠습니다.
아, 네, 알겠습니다. 그럼 이따 쉬는 시간 혹시 안 돼요?
그래서 이거 밑으로 이렇게 또 껴야 되나요? 또?
네, 밑으로 껴야 돼요. 쉬는 시간.
제가 할게요, 이따. 뭐 끼면 되겠죠.
밑으로.
네. 네. USB 이쪽에 연결했어야 되는데. Okay, so which parameters should we determine here based on our data, or which parameters should be fitted based on our data? Bandwidth, yeah. So the bandwidth, which is the variance of each Gaussian component, okay. But in this case, that parameter of our bandwidth or the variance of each Gaussian component is considered as a hyperparameter, okay? Because the parameters that are optimized based on our training data, should be kind of optimized, right? Based on particular data set, right? But in this Gaussian non-parametric or this kernel density estimation, we usually consider this bandwidth as a hyperparameter that we have to set beforehand, before training our data. So in this case, there's literally no training procedure, although we have some other additional strategies of optimizing this hyperparameter of this bandwidth parameter. But in this case, there is no training process, and this Gaussian envelope or the total overall density density model is just built by just summing up all these Gaussian little small Gaussian components. Okay, so in this case, there is no parameters to optimize through our training data. So in that sense, we can kind of view it as kind of parametric model, in a sense that we have fixed number of parameters, which are just 0 parameters to optimize in this case, right? But still, this is viewed as a non-parametric model because our model equation or mathematical representation of our model will actually change, which means, so if we have 10 different points, and then the total representation, the mathematical representation of the total density is the sum of 10 different Gaussian components, right? But if we have 100 points or 100 data items, and then the model will be represented as the sum of 100 different Gaussian components. So our model itself will actually change depending on the number of data. So think of the linear regression. Okay, even though we have parameters to optimize based on our training data, and then if we have a fixed number of dimensions, and then regardless of the number of data items, the mathematical representation will be fixed. As for example, right? So this is our linear regression representation, assuming that we have a 3 dimensions, right? So this representation itself will not change, right? But in the case of our kernel density estimation, the number of summations, I mean the number of these Gaussian components will actually vary or change depending on the number of data items. So that way, this kernel density estimation is is called the non-parametric model. Any questions so far? Okay, and yeah, there are many different tasks in the data mining methods, but I'm gonna just skip them. And this data mining is related to many different fields. Okay, so I'll just skip this part. And these are the types of data mining research, although they look quite obvious, but let me briefly mention a few things. So typically, in the case of supervised learning, we go for this higher prediction accuracy, but also faster computing time, and also this less memory is sometimes a critical or important concern. Okay, and also parallelization of the same algorithm. So for example, if you just implement k-means, which is the most basic clustering algorithm, but suppose you you implemented it based on the Hadoop or HD Hive or something like that, which is a big data framework, okay, which is a distributed file systems and so on. So in that case, so that simple implementation of this k-means based on this framework can be its own research. I mean the research paper. Okay, and also related to that, there are some non-standard but also quite large scale oriented research type is like on-disk data mining or machine learning. So the situation is, so the data to deal with is so big, so we cannot fully load into our memory because the data is too big. So how can we perform the same algorithm while the data still resides in the memory? In the disk instead of in memory. So in this case, we have to think of how these data are stored in our disk. Okay, so you guys know, like when evaluating or measuring the performance of the SSD drive, and then typically there are several different scenarios of a read and write, of course, and also like random access or sequential access, right? Sequentially reading those memory cells in the SSD can be quite much faster or not compared to the random access of our SSD, right? So those different types of considerations will be also incorporated in this type of research. So although it's not a big or really like widespread research areas, but I know several different researchers and professors in other universities are focusing on this kind of application in the data mining area, and also those papers focusing on the largest scalability can also be easily published in the data mining database domains, okay, like Sigmod, VLDB, and ICD are 3 major conferences in this area. And just for that, just to give you an idea about these terms, these pattern recognition. Pattern recognition is almost the same as machine learning, like the supervised learning or classification or regression. But in general, this pattern recognition belongs to the electrical engineering disciplines instead of rather than the computer science. Okay, so pattern recognition or yeah, signal processing. Yeah. So these are belonging to those electrical engineering disciplines, but they study different types of problems, but their research topics are highly overlapping with machine learning and data mining as well. Any questions so far? Okay, then let's move to the next chapter. Okay, so yeah, in terms of the target variable to predict based on the input feature vector, so the types of target variable is continuous, or this quantitative variables, or this qualitative or categorical variables, right? And at the same time, there is a third type of a target variable, or in general the variable type, which is called the ordered variable. So if you consider like blood pressure, then blood pressure can be represented as 108. Yeah, I'm not sure about the exact unit of this blood pressure, but yeah, this is a real value, right? But this value may not be reliable, so sometimes we just discretize it as a low, medium, and a high blood pressure when the blood pressure is less than 80, or between 81 and 120, or more than 120. Yeah. So in this case, these are discrete variable, right? But not a categorical variable, right? So these variables, I mean, it would not be optimal to represent this type of a variable as a one-hot vector, right? One-hot vector, because this is a kind of subtle, but I think it's a quite important issue when, especially dealing with some novel problems. Yeah. So the target variable that we want to estimate is like this type of variable, ordered but discrete variable, and in this case, we have two different methods of constructing our loss function. If we use the categorical variable and their loss function, such as softmax, okay, softmax loss, and then of course we will just encode them as a one-hot vector in a three-dimensional space corresponding to L, medium, H, right? So in this case, because this one is mainly for unordered categorical variable, so suppose our target variable is a low one, such as 100, but now our softmax probability distribution is, for example, 60 and 30, 60 and 10%. Okay, and then what is the loss in this case? Because this one is a target variable, and so negative log likelihood of this guy, right? So this is the loss, right? So in this case, so this is the loss, and intuitively the model thinks the most likely answer as their prediction will be medium, right? But what about this case? So in this case, our model is thinking that the high category, or this high value is our prediction output, right? But what about the loss? Loss is still the same as this case, right? Okay, so in the case of using a softmax or categorical variable-based loss function, and then these two will be treated in the same manner from the perspective of our model. Okay, so and alternatively, we can use the regression loss, for example. So we can just, I mean, it's a kind of an arbitrary choice that can be improved by considering some other aspects, but let's suppose we just use this target value as a 60 and 100 and 135. So we just discretize each level into a specific value, right? It can be viewed as like a median or the mean value of the actual observations belonging to that category, right? So in that case, we can just utilize this regression loss, such as L1 or L2 loss. Okay. So in practice, you can use both strategies, but in terms of the behavior of the predicted outputs, if you use this regression loss, okay, regression loss, and then the model will tend to generate the prediction output as the kind of middle value across this entire range of our value. So yeah, in general, in this case, yeah, the model will likely predict the target value as maybe 110, for example. Okay, because yeah, on average, I mean, if we just predict our target value as some kind of middle value, and then yeah, if we are not sure, and then this middle value will be the best strategy to minimize the regression loss, right? Okay, but in this case of a categorical kind of representation or model building, and then we don't know. I mean, we don't know which level of an outputs will be predicted. I mean, generated as a predicted output. Okay, so in this case, yeah, the distribution across different levels, yeah, the distribution may be closer to kind of a uniform distribution in terms of the predicted output. Okay. Okay, so yeah, let me show the actual example that I experienced. Let's see. So I personally do the research on this colorization, automatic colorization of the given grayscale or just an outline image, and then yeah, these are some of the result examples from the recent research with some of my students. And so here, yeah, it is basically predicting the color value in terms of their RGB value for each of our pixels. So given a grayscale image, our task is to predict the pixel-wise color value or RGB value. Okay, so yeah, the natural kind of formulation of this will be the regression, right? Because our pixel value, although they are limited, and also those pixel values are kind of an integer ranging from 0 to 255, but we can kind of view it as a continuous real value, and so it will be more natural to use a regression loss. Okay, but in this case, the regression loss tend to give us the model that predicts just a kind of a little bit muddy, just a gray colored or gray looking images, because just a predict generating the kind of middle color that just have maybe 128 for each of our RGB channels, that will give us like the small, in general, the smallest prediction error, because it is a middle value, right? But if we predict or generate a really extreme value like a 000, which is a really black, or 255, 255, 255, which is a really pure white, and then in that case, if we happen to have an error, and then this error might be really big, right? Because we picked up the extreme value out of unknown, compared to this unknown value. Okay, so the alternative approach is to use the classification loss in this case. Okay, so in this case, how can we make this problem as a kind of a classification over different categories. So similar to blood pressure case, we can just discretize each of our RGB values. So for example, for our channel 0 to 255, and then maybe we just chop them off into maybe 10 different intervals. Okay, and in that case, for our channels, we are predicting specific categories among 10 different categories, right? And we can do the same thing for blue and the red, the green channels, right? So that could be another kind of alternative way. And in that case, we empirically experienced that or observed that our predicted result is no longer be like a gray-looking images, which is really like a boring. So it is more kind of a vivid, or the images that has a specific color pattern. Okay, so that is because this classification, because of this classification loss. Yeah, and also related to this issue, in this case, we do the pixel-wise prediction, right? But for each prediction, we are not just predicting a scalar value, but we are just predicting a vector form of a value, because we are generating RGB value, right? So in this case, in this previous example that I described, I just discretized RGB values separately or independent, right? And then perform this classification on each channel. But more, better or desirable kind of way of discretizing this type of an output is doing vector quantization instead of a scalar quantization. So in the case of quantizing or discretizing our channels ranging from 0 to 255, and then these are still the scalar value, and then we can discretize them into 10 different regions or intervals, right? And then we do the same thing on blue and the green channel. So that is the most naive way of discretizing this value. But what about just discretizing those vectors as it is? So in this case, yep. So the vector quantization is also quite useful technique, and I personally view it as almost similar to the clustering. Okay, the clustering is, suppose we have RGB as this three-dimensional space, and then for each pixels, and then their pixel value as a set of these RGB value as a three-dimensional vector will be corresponding to a specific point at a particular position, right? So suppose we collect all the pixels from our training data, okay? So for example, we have 100 images, and then each image has the resolution of 20 by 30, and then we have 600 pixels in total per image, right? And then we have this many number of pixels, right? And then suppose we just draw these each of these pixels in the three-dimensional space, and then somehow they are represented in this form. Okay, so in this case, we can discretize this guy into this form, right? So this is a three-dimensional space. So this thin line should be really the plane that separates the entire regions into one of these regions. Okay. So in this case, this region is discretized into cluster 1 or level 1 and 2 and 3. So here in this vector quantization, there is no really ordering information. So ordering information is gone, but in this case, we can discretize continuous or real valued three-dimensional vectors into one of these regions that we define. Okay. So yeah, we can do this type of a quantization. Yeah, given this set of multidimensional vectors. Okay. So in this case, our problem or our task is to generate a single classification output for each pixel. So in the case of previous RGB channels, treated or dealt with separately, and then we perform the classification on each of these three channels, right? But in this vector quantization case, three-dimensional vectors are mapped into one single or one scalar discretized value, whether they are 1 or 2 or 3, or if they are treated as an unordered variable, and then they will be represented as a categorical variable that has three different possible values or categories. So in this case, for each pixel, we will just generate the classification, a single classification output. Any questions so far? Okay, and also, let me also add one other possible strategies to properly handle this ordered variable. Properly constructing the loss function to handle this discrete ordered variable is still on open research areas, I think. So there is no really single best solution, but I saw some other solution where we apply some different loss function as follows. So in this case, let's go back to this blood pressure case. So suppose we have this kind of output, this kind of discretization into these three different levels or regions. And then suppose your ground truth value is somewhere over here, for example 65. Okay, so in this case, suppose your regression based output probably as the direct output of this linear layer, for example, without any nonlinear layers such as nonlinear units such as sigmoid or softmax. Okay, and then your predicted value is 58. So in this case, what will be the loss when considering them as a discrete value? The loss should be 0 in this case, because they are belonging to this low level, right? And our predicted value is also belonging to the same category. So in this case, the loss will be 0, right? So in this case, we can also think of our new loss function considering this, okay, as follows. Okay, so this kind of one-sided loss, or if it is this middle value, or this medium value, which is bounded in both sides, then our loss function could be this guy, right? So we have no problem of applying this type of a loss function. So in this case, it will not necessarily try to fit the exact value of our ground truth. So typically, in the case of the standard regression loss, if the ground truth value was a 65, and then if our predicted value is a 58, our regression-based loss will try to move or increase that 58 into 65, right? So in the case of on the other hand, this type of a loss will just be fine even when they have some discrepancies or differences in this case. So that kind of strategy will may give you kind of performance improvements or like more reliable kind of, prediction outputs. Okay, so the example, one kind of example of this case, another kind of example, it could be like traffic kind of estimation or prediction. So this is a one kind of problem that I personally work on with some of my students. So we try to predict some future velocity of a particular road. So in this Anamogori, so what will be the amount of traffic, or what will be the average car speed in terms of a kilometer per hour and something like that. Okay, so we want to predict that value after 5 minutes, or after 10 minutes, or after an hour, based on the current observation data, right? So in this case, how can we measure this average speed? Okay, so someone may just watch or monitor the surveillance camera and then maybe manually calculate their speed. But typically, as you know, there is a special camera that can measure this velocity of a particular car, right? And so we can use this kind of measure, right? So in that case, if the road is really, the road situation is really good. I mean, there is literally no traffic. And sometimes a single car may run really fast, but sometimes some car may go really slow, obeying the speed limit. Okay, so in that case, it doesn't mean, it wouldn't be that much meaningful to predict that specific value at that particular time point that was collected, right? So in this case, this type of a loss may give you like a better overall accuracy, or the prediction accuracy for the test data. Okay, so this is another kind of another still basic kind of approach that can deal with this ordered variable, but there are many other, many different more advanced techniques that can handle this type of a problem settings. Any questions? Okay, so here are some terminology, but I'm gonna just skip them. So there are many different supervised learning methods. Okay, and and also this because we discussed about this non-parametric model, this k-nearest neighbor. K-nearest neighbor classifier is also representative method of non-parametric methods, right? Because it doesn't have a fixed number of parameters, and also the model representation. If we imagine some specific or fixed like representation of alpha 1 times x1 and so on, right? So that k-nearest neighbor classifier doesn't have a specific or fixed form to represent the classification model. So in that sense, it is also viewed as a non-parametric model. Okay, and probably you guys are familiar with this logistic regression. But today, I'd like to discuss a little bit details on this discriminant analysis, which includes a linear discriminant analysis, or quadratic, or flexible, and so on. But I will just focus on this linear and the quadratic one. And at a high level, I want to emphasize that these two models have an important differences. Okay, so this one, so you guys, we discussed some different types or different classes of machine learning methods, whether they are parametric or non-parametric, and also, similar to this, high-level kind of taxonomy or classification or categorization of our different machine learning methods. There is another important criteria to split the classification methods into two, which is like generative model, and I believe it's a discriminative model. Discriminative model. Okay, so yeah, in the context of supervised learning, such as a binary classification or multi-class classification, yeah, this criteria or the notion of whether a given method is a generative model or discriminative model is, yeah, an important one. Okay, so we will see what are the main differences and what are the main characteristics of these two different methods. Okay, so yeah, you guys know, yeah, this linear regression setting, and yeah, I will just quickly go through these by just pointing out a few of the important part out of many slides. So yeah, why do we perform the regression, or why do we train our regression model? So typically in the machine learning, the main purpose is the prediction. Okay, so that's why we reserve or set aside our validation data that is excluded out of our training data that will be revealed to our model, right? And then we evaluate the model performance based on our unseen validation data, right? So that is because our main goal is to predict this target variable for unseen data, right? But at the same time, this regression or these supervised learning methods can be also useful for so this inference. I mean, in the context of machine learning or deep learning, this inference is also almost the same thing as this prediction, right? And also this inference, I feel that the term inference is often used the same as like forward propagation, right? Sometimes we just say the word of an word inference as the performing the forward propagation of a given input, right, on the neural net. But here in this case, in this slide, this inference is more of interpretation. Okay, so so interpretation is like it's more about the retrospective retrospective type of an analysis. So given our data, for our target variable, which one is the most which one of our input variable is the most influential or the most closely related to our target variable? Okay, so those kind of identifying or understanding the relationships between our input variables and output variables. Yeah, sometimes this one itself can be our main task rather than just trying to predict some unknown cases. So in this case, how do we perform this inference or this interpretation? Okay. So in this case, if we use the linear model, and then our linear regression coefficient is learned in this manner. Okay, so in this case, we can easily see that. I mean, the most influential variable is x2, right? And next to it, x1 and x3, right? And also, these two are positively related. If x2 is increasing, then due to this positive coefficient, the y will also increase, right? And then, but in the other case of x3, so in that case, it has a negative influence, right? So this type of although it looks quite simple, but this kind of analysis or interpretation of our model have been widely used in a statistical literature or areas. Okay, but it's not as simple as this this kind of identification of the learned coefficient. But also, when if you studied this probability and statistics at an undergrad level course, and then this regression problem is really is formulated based on this generative model that I will describe in the later part, which is like our y value, okay, has some underlying kind of formula or underlying distribution, okay, underlying distribution that follows like, see, yep, this kind of a linear relationship with respect to our input variable, and also some noise part, right? So this part can be viewed as a deterministic, right? So even though we do not know, but beta 0 through beta p, where p is the number of variables, okay, or the number of features or number of dimensions, okay. In this case, even though we view these beta 0 through beta p are constant but unknown one that we want to identify or we want to find out, right? But still, those these features can be modeled as a random variable that follows a specific distribution, and also this epsilon value, or this error part is also modeled as some random variable. So typically this epsilon is following the Gaussian distribution having a zero mean and some some standard deviation or the variance, right? Okay, so in this case, the important difference of this kind of approach or this kind of perspective from the typical kind of least squares fitting of our linear regression. So for example, if you're familiar with the normal equation or gradient descent based linear regression kind of fitting or training, so there is no notion of like random variables at all, right? So we just randomly initialize those parameters, and then based on the gradient descent, we just perform this iterative update. So there is no notion of this random variable at all in this process, right? But still, this this linear regression have been heavily modeled from this statistics community as this generative process where those x and these y or target values are also the random variable, and then when these random variables are combined with a specific linear regression, linear combination coefficient, together with this error term, which is also a linear, random variable. And then in this case, whole or entire kind of analysis kind of strategy or approaches are becomes quite different from this gradient descent one. Okay? So although I'm not gonna cover all the details, but sometimes, I mean, if you just run this linear regression by using the statistics software such as in R, okay, and then in the case of running the linear regression using R, given a particular data, and then it gives a bunch of different values, which is also related to some hypothesis testing and so on. So for example, whether this beta 0 is 0 or not. Okay, so in general, if we perform our gradient descent, and then this bias will be converged into some non-zero value, and suppose that non-zero value is, for example, 2, okay, given 3x plus 2, okay, And then, yeah, we can kind of think again or question, okay, raise the question about, okay, is this value of 2 really like non-zero value, or that is just a 0, yeah, originally when, yeah, although we do not know, yeah, when considering their true generation model, okay, true generation model of y given these x's, this is really 0, but this one have been, yeah, this one happened to be, yeah, converted into 2 based on our erroneous training data. Okay, so in that case, we can perform hypothesis testing that this bias is really 0 or not. Okay? And also, we can do the same hypothesis testing with respect to beta 1 and beta 2 and so on. And then what's the meaning of it? Okay, so yeah, what's the value of applying this hypothesis testing on this resulting linear regression output or linear regression coefficient? So this can be used to answer this kind of question. So suppose we perform hypothesis testing of beta 1 is equal to 0 or not. Okay, so this is the null hypothesis, and this is an alternative hypothesis. So yeah, So I assume that you guys have some familiarity with the undergrad level probability and statistics and their hypothesis testing stuff. Okay, but if you are not, then it may not make much sense. But yeah. So in general, the high level story is, suppose beta 1 is, the converged parameter value is, for example, 0.8. But can we trust that, okay, x1 is really influencing the y value with the this amount, with the positive influence with the proportion amount of 0.8, or will it be just an error or coincidence based on our limited or noisy data? Okay, so it should have been really 0, but our data just gave some non-zero value. Okay, so can we answer this type of a question? So yeah, intuitively this question is like like whether this variable itself, or x1 is related to our target variable or not. Okay, so yeah, we can kind of answer this kind of question by performing this hypothesis testing. Okay, so in this sense, in this case, yeah, this inference is no longer be trivial. Okay, so it's not just a, okay, so it is related, and they are positively related, and the proportion ratio is 5. So the analysis is not that simple as this. Okay, so if you're interested, and then I highly encourage this, reviewing the undergrad level probability and statistics, and most of these undergrad level books of this statistics will have their own kind of big one or at least 1 or 2 big chapters on this regression and also related hypothesis testing. Okay, so again, this inference or interpretation may not be that simple, and so it will be also interesting part. So in this case, more kind of convincing or practical kind of example would be something like this. So suppose we measured, the measure of the PM 2.5 or PM 10, okay, which is the degree of this air pollution, okay, and then suppose we additionally collected some other independent or input features, such as a temperature or humidity and many other things, okay? And then we can perform the regression test to predict PM 2.5 or PM 10, right? But still, we want to have, we want to answer the question about, okay, even though I collected and used a bunch of these input features to predict the PM 2.5, but is this variable really correlated or influencing the PM 2.5, right? So we want to know about it, right? So this type of question can be addressed through this type of process. Any questions so far? 네.
제너레이티브 모델이랑 파라메트릭 모델이랑 하고
관계가
프리퀀티스트 어프로치 다 같은 말인 건가요?
세 개 다 다른 건데. 그러니까 다 다른 기준이에요. 그러니까 파라메트릭, 난파라메트릭은 아까 얘기했던 것처럼 그게 이제 뭐 확률 모델에 기반하느냐 안 하느냐의 차원의 문제가 아니라 아까 얘기했던 것처럼 어떤 딱 픽스된 식으로 딱 나타내질 수가 있어야 되고 우리 모델이. 네, 그 다음엔 역시 마찬가지로 그에 따라서 이제 픽스드 넘버로 파라메터를 가져야 되는 형태가 이제 파라메트릭 모델이고 그렇지 않고 데이터에 따라서 이 식 자체도 바뀔 수 있고 그에 따라서 이제 파라메터 수도 바뀔 수 있다. 그러면 이제 그게 이제 난파라메트릭이 되는 거고요. 그다음에 디스크리미너티브, 제너레티브 이쪽은 아직 뭐 조금 설명을 하진 않았지만 그 차이는 이제 여기서 보는 것처럼 이제 그 약간 우리가 리니어 리그레션 혹은 로지스틱 리그레션을 뭐 이제 일반적인 머신러닝에서 배울 때 뭐 그레디언트 디센트로 이렇게 한다 뭐 이렇게 배우잖아요. 그럼 거기서는 어떤 그 이제 x 그러니까 인풋 변수나 이제 y 혹은 그 타겟 변수가 어떤 확률 모델을 가지는 어떤 확률 모델을 가지는가에 대한 가정이 전혀 없잖아요. 약간 그런 거를 디스크리미너티브 모델이라고 할 수 있을 것 같고 애초에 이제 여기서는 아까 봤던 것처럼 또 이겼을까? 네, 이 y나 어떤 x에 대해서 애초에 어떤 정해진 그 probability distribution이 존재해서 거기서부터 뭔가 샘플링이 된 형태로 우리 데이터가 수집이 됐을 거다. 그리고 그거에 대한 이제 언더라인 모델, 그 제너레이션 프로세스를 관장을 하는 어떤 특정한 이제 정해진 모델이 있을 거고 그걸 우리가 이걸로 가정하고 물론 그 모델의 이제 파라미터를 우리가 또 에스티메이트를 내부적으로 하겠지만 그런 식으로 뭔가 얘네들이 생성된 어떤 그 probability distribution 거기 그러니까 샘플이 이제 그 뽑혀진 그 모수가 underlying probability distribution 있을 때 약간 그걸 이제 제너레이티브 모델이라고 하고요. 그래서 확률적 모델이 아닌 제너레이티브 모델은 없는 셈이라고 보면 되고요.
일반적으로 말하는 프리퀀티스트 어프로치
네.
같은 말이라고
그거랑 또 다른 말이에요. 프리퀀티스트 베이지한 그거는 이제 뭐 ML이니 이제 뭐 map 혹은 maximum a priori 뭐 여러 가지 이제 조금 뭐 이야기가 또 나오는데 이제 중요한 건 여기서 이제 베타 0, 베타 1 이거에서 보면 이제 이게 여기서 아까 x1에서 xp까지의 이 값들은 얘네들이 이제 우리가 인풋 피처들은 어떤 특정한 이제 랜덤 베리어블이라고 가정을 할 수 있어요. 뭐 할 수 있냐 없냐를 누가 결정해 준 건 아니지만 일단 할 수 있다고 치고. 근데 이제 이 식에서 중요한 거는 이제 베타 0부터 베타 p는 쟤네들은 이제 하여튼 모르는 파라미터긴 하지만 그 파라미터를 이제 상수로 보는 어프로치가 있고요. 상수. 그러니까 우리가 몰라요. 모르지만 쟤네들은 하여튼 상수예요. 네, 그런 어프로치가 이제 프리퀀티스트 어프로치고 그다음에 이제 베이지안 어프로치는 쟤네들도 약간 어떤 디스트리뷰션을 가진다. 그게 이제 베이지안 어프로치가 되고 그러니까 그 말은 무슨 소리냐면 우리가 데이터를 뭐 그레디언트 디센트를 통해서 이제 파라미터를 이제 옵티마이즈를 하죠. 그러면 그 옵티마이즈된 파라미터는 말 그대로 그냥 상수로 그냥 딱 정해진 값으로 나오잖아요. 그게 이제 ML이나 이런 거를 뭐 직접적으로 뭐 맥시멀 라이클리후드를 써갖고 이렇게 한 건 아니지만 그게 어떻게 보면 프리퀀티스트 어프로치와 그 애를 좀 같이 한다고 볼 수 있고 그러면 약간은 그게 아닌 베이지안 어프로치는 어떻게 되느냐? 뭔가 우리가 이제 에스티메이트 하고자 하는 파라미터를 우리가 예측을 하거나 이제 최적화를 하는데 그 값이 상수가 아니라 우리가 이제 뭐 다 그레디언트 디센트든 무슨 알고리즘이든 이제 옵티마이즈를 이제 데이터에 기반해서 했을 때 나오는 어떤 최종 결과물이 최종 결과물이라는 건 뭐냐? 얘네들에 대한 단서 혹은 정보 베타 0, 베타 1 얘네들이 어떤 정해진 상수로서 딱 알고리즘의 아웃풋으로 나오는 게 아니라 쟤네들이 어떤 디스트리뷰션으로 나오게 돼요. 디스트리뷰션. 즉 이제 그레디언트 디센트를 돌리면 베타 0는 3이다 이렇게 나오잖아요. 콤보지에서 3이다. 그냥 숫자 하나죠. 거기는 어떤 랜덤 베리어블이라는 노션이 없어요. 근데 이제 그레디언트 디센트를 막 돌렸더니 우리는 이제 베타 0가 평균은 3이고 분산은 2인 어떤 디스트리뷰션이다 라는 형태로 나오는 그런 이제 그게 이제 얘가 랜덤 베리어블이다라는 가정을 처음부터 했기 때문에 그게 가능해지는 거거든요. 그래서 그게 이제 베이지안 어프로치가 되고 그러면 우리는 한 단계가 더 필요해요. 그러니까 실제 그래서 디스트리뷰션 그래서 뭐 얘가 평균이 3이고 이제 분산이 이제 2예요. 그러면 우리는 하여튼 뭔가 예측도 수행하고 이러려면 값이 하나가 필요하잖아요. 하나. 디스트리뷰션으로 얘가 말이지 그러니까 정해진 값은 아니고 얘에 대한 디스트리뷰션이 평균이 3이고 분산이 2인 어떤 그런 랜덤 베리어블이야. 그러니까 이 지금 주어진 데이터에 기반해서 내가 최대한 옵티마이즈를 했을 때 나오는 아웃풋은 나는 얘가 이제 랜덤 베리어블을 가정하기 때문에 싱글 밸류라고 너한테 주는 게 아니라 얘에 대한 이제 디스트리뷰션을 내가 데이터에 기반해서 잘 이제 해갖고 준다든지. 그러면 그 거기서 나오는 디스트리뷰션, 그러니까 어떤 뭐 0이가 모은 데이터로는 얘에 대한 디스트리뷰션이 평균이 1이고 분산은 4로 나올 수 있고, 또 내가 뭐 철수가 모은 데이터로는 또 그걸 피팅을 했더니 뭐 그레이디언트 디센트나 이런 걸 통해서 이제 뭔가 했더니 이제 얘에 대해서의 디스트리뷰션은 뭐 평균이 3이고 이제 분산이 2인 형태로 디스트리뷰션이 데이터에 따라서 다르게 나올 수 있는 거예요. 근데 이런 경우 근데 그것만으로는 부족하잖아요. 우리는 하여튼 뭐 하나 값을 딱 선택을 해갖고 우리 이제 옵티멀한 모델이 뭐다 이거를 가지고 뭔가 예측도 하고 뭘 해야 되잖아요. 그래서 이제 거기서 이제 한 단계가 우리가 더 필요하고요. 그러면 그 한 단계가 더 필요한 게 이제 여러 이제 스트래티지가 있는데 그 베이션 어프로치에서는 그러니까 일단 옵티멀 파라미터의 형태가 그냥 특정한 싱글 상수값이 나오는 게 아니라 어떤 디스트리뷰션 형태로 나온다. 그럼 그 디스트리뷰션에서 우리가 어찌됐건 한 값을 골라내야 되는데 그 한 값을 골라내는 방식을 이것만 그냥 Okay, so yeah, in terms of a Bayesian versus frequentist approach, so these parameters themselves are considered as a random variable. So after fitting these parameters based on our data, so these random variables will be given as some distribution, okay, as an outcome of our optimization based of our data. So suppose for say data 0, suppose that this random variable has the probability distribution of something like this. Okay. So of course this PDF will sum up to 1. Although I mean typically those parameter distribution will be modeled as a unimodel, but yeah, it is still possible, right? For as a valid random variable. So in this case, which one will be our best strategy to if we have to pick up the single value out of this distribution? The first strategy will be to choose this guy or this guy. So yeah, so it is 1 and maybe 3. Okay, so in this case, we can choose 3 as our optimal single value, right? So in this case, it's corresponding to the case where we used the specific strategy called maximum a priori. Is it right? Maximum a priori. Is it right? 포스티리어 같은 단어가 들어왔네. 맥시멈 포스티리어요? 맥시멈 A 포스티리어예요? 이거 이름이 뭐더라? 네? 맵이 이게 풀네임 뭐죠? 맥시멈 포스티리어? 그럼 이 A는 맥스에서 거기서 A가 온 거야? 이게 아닌 것 같은데? 이건 포스티리어인데 이건 프라이어가 아니라. 어쨌건 네. Okay, so one strategy is to choose such value that has the highest probability value, right? And another strategy, I forgot the name, but another strategy is to choose the mean value by using this distribution. So what would be the mean value? So mean value is somewhere over here. Okay. So mean is computed as this guy, right? But intuitively, the meaning of it is if this guy is mean, okay, so this guy is mean, I was intending the notion of the median. Okay, median. So yeah. So suppose we chose some value that has the probability on the left side is exactly 1/2, and the right hand side is accordingly exactly 1/2, right? We can choose that value, right? So if it is a kind of a discrete discrete value. So for example, if our random variable for our parameter are actually some discrete value, although yeah, it is not not practical or not common. But suppose we have our it's a little bit unnatural, but suppose we have these 5 different possible values that have the same probability for each value. Then the best strategy would be to choose the median one among our samples that we obtained. Right? Although we have to define the underlying probability itself, but not these samples. Yeah, but actually this sample-based approaches or sample-based kind of inference or this kind of approach is also called the Monte Carlo kind of simulation and sampling method. Sampling-based some machine learning method will actually model this underlying distribution based on these some random samples. But anyways, I will not talk too much about it because I do not know very well about it. But anyways, we can choose this median value, and so that is another strategy. And this kind of mean value, choosing this mean value with respect to this given underlying distribution, so that is another strategy, right? So we basically have 3 different strategies. So which one is the best one? It really depends on the problem. Okay? So each choice or each strategy has its own pros and cons. So it's no nothing like which one is correct or incorrect, or which one is better than the other overall. It's not like this type of problem. But anyways, at a high level, I mean the point is that if we discuss, or if we are like Bayesian believer, and then our parameter estimation will be given as the distribution of that based on our data, and then from that distribution, if we want to have a single value, and then we need additional steps such as these. Okay, okay, so 답이 좀 됐나요? So again, back to the frequentist approach. Frequentist approach is assuming that these parameters are constant, although they are unknown, but they are just a single fixed constant value, which is not random variable. Any other questions? Okay, then let's take a break for 10 minutes.